Hello, AP Chemistry students, and welcome to Unit 3 of AP Chemistry, which covers gases. And in this video, we're going to go over the basics of kinetic molecular theory, which covers how gas particles behave with each other, and we'll later see the math behind all of these theories. So the first thing that we're going to say is that gas particles, their actual volume is so small. And what this means is that your volume of your container is going to be equal to the volume of your gas. Okay, the actual space that the particles on the molecular level or on the atomic level actually occupy is so small that we can just say that it's negligible. We're going to say that gas particles are so far apart that they undergo no intermolecular forces, and gas particles are in continuous random straight line motion. The collisions between gas particles are completely elastic, which would be like if you have a tennis ball and you drop it and it would bounce just as high as from where it started, which we know in real life that doesn't exactly occur, but the collisions between gas particles don't lose very much energy, that they're nearly elastic. And then this is important, there'll probably be a question on the test, but the average kinetic energy is the same for all gases at a given temperature. Okay, temperature is simply a measure of kinetic energy. And so if gases are at the same temperature, well, then they have the same kinetic energy. It doesn't matter on the identity of the gas, it matters on the temperature of the gas. You will be very good at pressure conversions, and if you check out your laminated periodic table, there will be some conversions. We've seen from last unit 8.314. This we will typically use when there are joules involved. In this unit, and really only in this unit, we're going to see that 0.0821, which you might call 0.08206. And then if we have torr, we can use 62.36. And 1 atmosphere of pressure is equal to 760 millimeters mercury and 760 torr. For manometers, if it's a closed manometer, which this is not on the test, don't worry about this, but I like to cover it just in case it did show up on the AP test, even though it really shouldn't. But it's definitely not on my test. If we have a closed manometer, the pressure of your gas is going to be equal to the height of your mercury that is being pushed from the pressure from your collected gas. If your manometer is open to the atmosphere, so we have atmospheric pressure pushing down, we want to ask ourselves, does the collected gas or does the atmospheric gas, which one is pushing down more or generating more pressure? Well, in this instance, it's very clear that the atmospheric pressure is pushing down more, and I know that because they are pushing the mercury even more than the collected gas. And so the pressure of your collected gas is going to be equal to the pressure of the atmosphere minus the height of the mercury. Conversely, if we have our collected gas pushing down just a little bit more than the atmospheric pressure, that means that the collected gas must have a higher pressure. And so we will take the pressure of the atmosphere plus the height of the mercury column. Okay, I wouldn't worry about those, but that's not bad information to know. What I would worry about is the rest of these notes, where we want to know the general properties that gases obey. And so gases will completely fill their container. If someone in your house is making chocolate chip cookies downstairs, you will certainly smell it at some point because the vapor or the gases from those chocolate chip cookies will expand to fill your entire house. Solids and liquids do not behave this way. While you can compress solids and liquids, gases are the most compressible. Their particles are so far apart that if we compress them, we can get them closer together. The pressure, and you need to know this, the pressure inside a container is not caused by the particles hitting each other, but rather it's caused by the gas particles hitting the wall of their container. If the volume of the container is decreased, this means gas particles will hit the wall more often, and that will increase your pressure. And on the same kind of relationship, if gas is heated, if you heat them up, you speed them up. And so the particles will increase in speed and the particles will hit the walls of the container with more force and more often, okay? That's often something that AP looks for, is that you would say that the collisions are more frequent and the collisions are more forceful. And then gases will completely mix to form homogeneous mixtures with other gases. Okay. There are 4 quantities to define a gas. One is the amount of gas, which we will measure in moles, and we use lowercase n to represent moles. Another would be temperature. If you're ever in doubt, temperature is always in Kelvin in this class. Volume. We'll go over later in the unit, but if you're ever in doubt, let's use liters. You may remember from Unit 1, if we did M1 V1 equals M2 V2, if you have volume on either side of your equation, then they don't have to be liters because ultimately they just need to be the same for the units to cancel. And then pressure, generally it's a good idea to get your pressure into something like atmospheres, which we will abbreviate ATM. As a general reminder, Kelvin, we will take the degree Celsius that is given. Often you're pretty much only given degrees Celsius, and we will add 273. If you care to know, it's technically 273.15 that we will add to get the Kelvin temperature. The reason why Kelvin is important is that Kelvin mathematically cannot be negative, and so it prevents from solving for a negative pressure or volume, and 2 of things that cannot exist. If you're curious how we know what absolute zero is, if you just graph temperature and then measure the pressure, you'll get a linear relationship with a y equals mx plus b equation. And what you can do is you can extrapolate it to see when does it cross the y-axis, and then that would represent the lowest possible temperature, and the Kelvin scale is based on that. Okay, I don't know that it's possible that anyone's ever gotten 0 Kelvin, but I know that they've gotten awfully close. Okay, standard temperature and pressure, STP. This is not standard conditions necessarily, okay? So this is different than standard conditions for electrochemical cell. If you remember us talking about my professor Dennis and how they decided that standard electrochemical conditions would be 298 Kelvin so that their labs were not cold, but STP conditions will be 0 degrees Celsius and 273 Kelvin and 1 atmosphere. Diffusion is the process of one substance spreading throughout another substance. A great example of that is if we have food coloring and water. You don't even need to mix water with food coloring. As long as they come into contact with each other, you will eventually get a homogeneous solution, and it's just that it takes some time. Now, how fast the dispersion occurs depends not only just on temperature, but on the molar masses of your samples. So gases with smaller molar masses, they diffuse faster and they effuse faster. And we'll get into effusion in just a second. But lighter molecules travel at faster speeds. And the speeds of molecules is actually kind of a massive number. So for example, hydrogen, which has a molar mass of 2 grams per mole, travels at nearly 2,000 meters per second. Where something a little bit heavier, like what you exhale as carbon dioxide, travels at about 20% of that at 415 meters per second. Still a massive number, but because it's so much heavier, it travels much slower. This is not necessarily a one-to-one ratio. There is a mathematical equation, so just because something has double the mass, you wouldn't expect necessarily half the speed. Effusion is specifically the movement of a gas through a small opening in a container. So you could imagine if you were on a plane and there was a small leak in a window, the gases that are leaving through that small leak in the window would be considered effusing out of your plane. And gases with smaller molar masses, because they travel more quickly, they just effuse faster. But with that being said, speed is not kinetic energy. Speed is how fast you are moving, and so that might be measured in something like meters per second, where kinetic energy is a measure of the total energy of movement. Gases at the same temperature have the same average kinetic energy. We've seen that. And gases with smaller molar masses travel faster. They effuse faster. They diffuse faster. We can add that here. They also diffuse faster. And what you want to be able to read, and these take a second to read, is something called a Maxwell-Boltzmann distribution. And what we have is, and I'm going to draw maybe in pink here, we've got oxygen, nitrogen, water, helium, and hydrogen. Oxygen has a molar mass of 32, nitrogen is 28, water, we can round it and say 18, helium is 4, and then hydrogen is 2. And so what you want to think about is, and if you're in AP Stats, maybe you've already gotten into this, is sort of like a normal distribution curve. That most of our particles are going to be traveling at that peak. And so I tend to focus just on the peak. So we've got oxygen, and I'll bring it down here. The oxygen molecules are traveling approximately 300, 400 meters per second, where our hydrogen molecules, because they're so much lighter, they're tending to travel way faster, closer to 2,000 meters per second. Okay, so yes, there's a probability that there are some hydrogen molecules at 298 Kelvin that are traveling up near 3,000, just like it's a probability, it's a low probability, but there's a probability that some of them are traveling, at the same speed of oxygen. But on average, most of them are in this middle range ballpark, according to this normal distribution curve. Okay, and we can prove that speed is not kinetic energy with a thought experiment, and we can imagine this situation. You could say that this is you, and you are going to stop each of these things. They're going the same speed. We have a semi going 30 miles an hour. We have a car going 30 miles an hour, and we somehow have a massive child going 30 miles per hour. And if you had to ask which one would you choose to get hit by, and out of the three, if you had to pick something, I'd probably pick the massive child. And so that's because although they are moving at the same speed, the child is certainly going to have less mass than the semi-truck. And if you've taken physics, you've probably seen at this point the kinetic energy equation that is equal to 1/2 mass times velocity squared. And so which above has the greatest kinetic energy? That's certainly going to be our truck. And because while all three are moving at 30 meters per second, the truck has the most mass, thus the most kinetic energy. And in AP Chemistry, we'll never have to mathematically solve out this equation, but it's still a good one that you may see at some point if you decide to take physics. Now, I believe the last thing, and I'm going to flip forward just to make sure we're at the last thing here, that I'm going to go over is Maxwell-Boltzmann distribution curves and how they may shift. So once you take calculus at some point, whether that's in high school or in college, depending on what math class you choose to take, is you will learn what an integral is. And what an integral is it's the inverse of a derivative, and it gives you the area underneath a curve. Okay, so we've got this curve, and there is some area here. And we're going to say that this area is constant. But we may change the curve, but the area is constant. And just for ease, I'm just going to say we have 100 molecules. Okay? And so we want to know what happens if you raise the temperature. So what's been drawn here is just baseline. Let's say we're at 298 Kelvin to begin with, and we want to raise the temperature really high. Well, we want to make sure that we're always kind of focusing on the average of our normal distribution curve here. And if we increase the temperature, I think that on average, most of our particles are going to have a higher speed. So I think that our curve is going to shift this way. Now, before you write anything down, just wait. A lot of people might say that, oh, you'll get the same curve, but it'll just be shifted over to the right. And it's not exactly that simple, because even if you increase the temperature, there is still a probability that some of our particles will have very low speeds. It's not likely, that's not what I'm saying, I'm just saying that there is a probability. So rather, if you shift right on a Boltzmann distribution curve, you're going to get a peak that on average has a higher x value, but it'll be more broad and spread out, where there's still going to be a probability that some particles are over there. Okay, and let me redraw this, that's really a cruddy picture. So we get it more broad and spread out, but on average, our particles have increased in speed. Now, if we lower the temperature, you may guess that the average speed is going to decrease, so I agree. So again, we're going to shift left. And because we can't go into a negative speed for our particles, that doesn't make much sense in this context, our curve, instead of being shorter and broader, it's going to be kind of smudged up here, and the average might be a little bit taller, and you're going to get something that looks like this. Okay, there'll be a higher probability at a lower temperature that our gas particles have lower speeds. And so our average is over here somewhere for most of our particles. Okay, those are definitely on the test in a week or so. So what happens if you change the molar mass? Well, if we change our molar mass, let's say we have a higher molar mass. I want you to ask yourself, at a higher molar mass, would our particles move faster or slower? And then if we had a lower molar mass, would our particles move faster or slower? At a higher molar mass, I think our particles are going to be heavier, and they're just going to move slower. And so their average speed is going to go down. And so when we shift to the left, our peak is going to get taller and skinnier, something like this maybe. And then if we lower our molar mass, our average speed is going to get higher, and that will cause our graph to be shorter but more broad. And so we might get something that looks like this. To finish up these notes, and I know I've been going a little bit slow, I just want to make sure we're good here, is I want to review how to convert pressure. So I'm going to look just at number 2, and I think you guys are going to be great at these. So we want to rank the following in decreasing magnitude. So decreasing is going to be largest to smallest. And when we go from largest to smallest, we're going to need to make sure we're all in the same units. So we're all in kilopascals, torrs, atmospheres, and millimeters of mercury. I'm just going to convert to atmospheres since that's the one that I'm typically most comfortable with. So 0.6 atmospheres, that one is good. I'm going to convert 75 kilopascals into ATMs. And I may use my honors chemistry periodic table. I may use this one. But I'm not sure if kilopascals is on our conversion for the AP chemistry formula sheet. But I'll just tell you, in 1 atmosphere, there is 101.325 kilopascals. And so we'll go from kilopascals to atmospheres. We'll grab those numbers. There's 1 atmosphere, and then there's 101.325 kilopascals. I'm going to get my calculator. Not the least bit concerned about significant figures here. And we are going to get 0.74 atmospheres. Now, the one that you'll definitely see a lot is torr in millimeters of mercury. If you remember from your days in honors chemistry, torr is named after millimeters of mercury, and specifically the guy that developed millimeters of mercury named Torricelli. And so they're just the same thing. So 300 torr, 1 atmosphere is equal to 760 torr, or millimeters of mercury. And so we'll just take torr to millimeters of mercury. There are 760 torr and I'm going to go to atmospheres. Goodness, sorry about that. In 1 atmosphere, 300 divided by 760, we get 0.39 atmospheres. And then for our last one, we'll take 350 millimeters of mercury. There's 760 millimeters of mercury for every 1 ATM. And there we'll do 350 divided by 760. And we're going to get 0.46 atmospheres. We want to rank them from largest to smallest. So I've done that one. 0.6 appears to be the largest, so 0.60 ATMs, which is bigger than actually I messed up. This one's 0.74. Sorry about that. We'll say that 75 kilopascals, since that was the original number, is bigger than 0.6, which is bigger than 0.46, which was 350 millimeters of mercury. And then our last one, which is 0.39 ATMs. If you've made it to the end of this video, congratulations. Send Mr. Payne a Schoology message and I will award you with bonus.